So the topic for today is how to estimate the error when using Gaussian elimination or the LU method, which is more or less the same thing, to solve linear equations. I'm on the wrong slide. Here we go. So remember, we're trying to solve this equation, a times x equals b. Now, things can go wrong. You may not always get the exact value for x, right? For example, when you do Gaussian elimination, when you do the row reduction process, you're going to be adding numbers together and subtracting numbers. You can get loss of significance errors there. Similarly, when you divide by a number that's close to 0, right, that could create problems. So in the case of a badly behaved matrix A, you may not get the, even though we're just doing linear algebra, you may not get a precise answer, right? So we still have to do error analysis, is my point, right? We still have to do error analysis, even though we're just doing linear algebra. So what we do is in order to help us analyze this, we define this auxiliary notion of error, the residual. The residual is not the difference between the difference between our approximation and the true solution. It's the difference between a times our approximation and the true value of b, right? If we have the true value of x, then a times x would be exactly equal to b. But since we don't, a times x will be something different than b, and this number b minus a times x, a, meaning the approximation to x, that'll be some number called r, the residual, and it's usually going to be non-zero, right? There'll be a difference. Okay, so r is the error in a times x, you might say, whereas e, as usual, is the error in x itself. It's the error it's equal to the true value of x minus the approximation to x. Note that the r and e are vectors here, right? They're both the residual and the error are actually vectors. E, for example, is a vector that consists of the error in each component of x. Now, it's interesting to note there's a nice simple relationship between the residual and the error e. So if we multiply the error by a, and then just replace e by xt minus xa, well, what happens if you multiply a times xt? Of course, you get b. And if you multiply a times xa, well, you get a times xa. But this is exactly the definition of the residual. So the conclusion is that a times e is equal to the residual. The error and the residual are related in the same way that x and b are. That, just as a times x equals b, so a times e equals r. Okay, so we got this relationship. Now, the reason this is useful is that r is easy to calculate, right? R is simply given by this. It's b minus a times xa. It doesn't involve any row reduction or LU decomposition or anything fancy like that. This is simply matrix multiplication. So we can assume that this is highly accurate, right? That r can be computed with high accuracy. Okay, so if we can get r with high accuracy, maybe we can use r to at least get an estimate for e, because r and e are related by this equation. That's the idea. Now, the trouble is, as I said, we can't always solve this equation exactly. In using the LU method or Gaussian elimination, we may have to settle for an approximation. However, the good thing is that we can use the same LU that we used to solve ax equals b. We can use the same LU to solve ae equals r, right? So we don't have to do any extra work for that, right? We can get the error estimate using the same L and U. And then, well, not only do we have a good estimate, well, reasonable estimate for what the error in our answer is, but if we have a good estimate for error, why don't we try to use that error estimate to try to improve our estimate for the solution? So that suggests an iterative method whereby we start off with an initial approximation to the solution using the LU decomposition or Gaussian elimination, and then you then calculate the residual and use the residual to estimate the error, right? So you can estimate the error in the residual using the same LU we computed earlier. And once we've got that estimate for the error, we then can revise our estimate for the solution by adding the error onto the old solution to get the new solution. And then you can repeat, right? Go back to step 2 and repeat steps 2, 3, and 4 as many times as you like until you think you've got a sufficiently accurate solution. Okay, so that seems like a good plan. In fact, it is. It is a good plan. So the question is, will this method actually converge to xt? Right? So for that, we need to show that e approaches 0. Right? As you iterate this method, the error vector eventually approaches 0. Now, since we're going to have to talk about things, limits and inequalities, right, getting error estimates and things like that, we have to introduce some notions of rough estimates for the size of a matrix, right? So this is going to be now a short digression on the issue of matrix norms. So a norm, it's kind of like the magnitude of a vector. It's just a slightly looser term. It doesn't maybe satisfy quite as many properties as a magnitude does, but similar idea. So what we'll do is we'll define the norm of a vector. By the way, the shorthand notation is you use double absolute value signs, right? So it's also kind of like an absolute value. It's not as precise a measure as absolute value or magnitude. So that's why we use the word norm. It's a bit fuzzier. But the norm of a vector will be equal to the maximum value of the absolute values of all the entries in the vector, right? So you just look at all the entries and take the one with a maximum absolute value, and that absolute value is the norm. For the norm of a matrix, it's a similar idea, only slightly more complicated. What you do is you look at each row of the matrix. So in this here, I runs through the rows of the matrix, and for each row, you add up the entries in the row. So J runs through the entries in the row, or in other words, J runs through the columns. So A sub ij is running through all the entries in the ith row of the matrix. You add up all the absolute values, and whichever row has the maximum sum, you take that maximum sum to be the norm of A. Okay? So similar definition in both cases. And one thing it means is that with this definition, we can say that as long as the norm of the error goes to 0, that will mean that, in fact, all the entries in E are approaching 0, right? If the maximum entry in E is approaching 0, that means all the entries in E are approaching 0. So we can use this notion to say, well, as long as the norm of the error is approaching 0, we can be sure that we've got convergence, right? That the iterations are converging to the true value because the error is converging to 0. Now, these notions of norm for vectors and matrices, they satisfy some simple natural conditions. This one is kind of like a triangle inequality. It says that the norm of A plus B is less than or equal to the norm of A plus the norm of B. This is essentially the triangle inequality, right? The norm of the sum of two matrices is no greater than the norm of one plus the norm of the other. Right? Pretty easy to verify if you want to give it a shot. By the way, this also works for vectors. I just wrote it out for matrices, but it's also perfectly valid for vectors. And then a similar one for multiplication, that the norm of A times B is no greater than the norm of A times the norm of B. Okay, so again, pretty easy to verify. Maybe a little tedious, but pretty straightforward to verify that. Okay, so these are really useful properties that we'll be using in showing that this iterative method actually converges to the true value. But the digression continues a little bit longer, so I got to do one more thing. Let me use these norms in order to show how they, well, in order to derive some formulas that relate E and R in terms of the norms of A. Okay, and B, for that matter. Okay, so we know that in principle, A times E equals R. That's exact in principle. So if we multiply by A inverse on both sides, we can say the error is exactly equal to A inverse times R. Now, taking the norm on both sides, we can say that the norm of E is less than or equal to, so now we're using that second inequality from the previous slide, is less than or equal to the product of the individual norms. Right? Now, this is significant because if the norm of A inverse is large, that might mean that we could have a small residual, but still have a bad error. Right? So it may be that A times our approximation XA really is close to B, so that the residual is small, but nevertheless, we could still have a large error in the in our solution X. Right? And that can happen if the norm of A inverse is large. Well, that could happen, for example, if when you're dividing, you're dividing by numbers that are close to zero. Maybe the pivoting wasn't entirely successful. Even after pivoting, you still ended up with numbers that were close to zero that you had to divide by. Another way to put it is you could say if the determinant of A is close to zero, well, the determinant is used in the theoretical formula for the matrix inverse, right? It's 1 over the determinant times the matrix of cofactors. And so if you have to divide by the determinant to get the inverse, then, if the determinant is close to zero, then the inverse is going to consist of large entries, and this might be a large number. Okay, so all those things could contribute to A inverse having a large norm, which would mean that we have to worry that even if we got a good approximation for A times X, that does not necessarily mean we got a good approximation to our solution. Okay, now I'm going to make just a slight modification here. I'm doing, a slight tweak of the formula. Divide both sides by the norm of the true solution, xt. Okay? And then on the right side here, I'm going to make a further alteration. I'm going to introduce factors of norm A over norm A. Right? So I didn't change anything. And now we can think of this as this factor, norm of A inverse times norm of A, times this factor. Now look more carefully on the right here. This denominator consists of the norm of A times the norm of xt. Okay? And this denominator here, well, if you multiplied A times xt without the norms, that would exactly give you B. So by the second inequality on the previous slide, A times xt is less, the norm of A times xt is equal to the norm of B, and therefore the norm of B is less than or equal to the norm of norm of A times the norm of xt. In other words, the norm of B is less than or equal to the norm of A times the norm of xt. Right? That means that if I replace a bigger denominator here by a smaller one, norm of B, potentially, that would only increase the value of the right sides of these inequalities. So by doing that, I preserve the inequality. If anything, I've only made the right side bigger by doing that, so we preserve the inequality. And now this is kind of the quoted result that we want to refer back to. So it says that the norm of E over the norm of the true value, this ratio is kind of like a relative error, right? The error divided by the size of the error divided by the size of the true value. Kind of a notion similar to relative error. Is less than or equal to, and now we got these two factors, norm of A inverse times the norm of A, and then this, which basically just depends on the residual. And the residual, of course, might change depending on your how good your approximation is. It's going to change in the course of the iterative method we were talking about. But this part is constant. This part depends only on A, it doesn't even depend on B. And so for that reason, because these two factors appear in this important formula that gives us a bound on the error, that product is called the condition number of the matrix. So the condition number of the matrix is the norm of A inverse times the norm of A. And if that number is very large, That's kind of bad because, again, that would mean that even if you have a small residual, even a kind of a small relative residual, right? If you take the error in B divided by the true value of B, it's kind of the relative residual error. If this factor is large, that could still mean that your relative error in E is large. So even a small relative residual error could correspond to a large error in the solution if the condition number is large. Okay, so the condition number is often taken as a kind of a one-number summary of how badly behaved a matrix is with respect to row reduction and Gaussian elimination. Okay, now I think, yeah, okay, so that's the end of the digression. With those results, I want to return to thinking about this iterative method for solving linear equations to greater accuracy. Right? No, so remember, we're trying to solve this equation, a times x equals b. In doing this, we work out the LU decomposition of A. And the trouble with the LU decomposition of A is that it may not be exactly equal to A, right? For all the reasons we talked about, truncation errors and loss of significance errors. LU may only be an approximation to A. And it may be a worse approximation in situations where A has a bad condition number, a large condition number, or we say A is ill-conditioned. In those cases, LU may have significant differences from A, right? They may have significant discrepancies. So we define P to be the error in our approximation. Oh, by the way, N, I'm going to use N to denote L times U in what follows, okay? Because I'll be writing that a lot. And P will be the discrepancy between N, which is our approximation to A, and the true value of A. By the way, I found this a little irritating. Normally, the error is the true value minus the approximation. Here, it's reversed. It's the approximation minus the true value. So the sign is reversed. That actually turns out to be convenient. For some formulas that will do, but I find it a little irritating. Anyway, what that means is that you can break A down into N minus P, not N plus P, but N minus P. Okay, so remember, N is our approximation to A. It's N is a well-behaved matrix, right? That in a sense that it's easy to get solutions using N, right? Because it involves forward substitution and backward substitution, and those are both easy to do. So we can assume that answers can be calculated reliably, precisely, using N, or L times U, whereas solving equations involving A, we're only going to get approximations. In fact, when we try to solve the equation A times x equals B, what we're really doing when we use the LU method is we're solving N times x equals B, right? Because we're replacing A by L times U, and L times U may just be an approximation to A. So the approximate solution that we get for x, it will be an exact solution to N times x equals B, but only an approximate solution to A times x equals B. Okay, so for our initial approximation, when we're trying to solve this, this linear equation, our initial approximation xa will satisfy N times xa equals B. Right? We can assume that that's precise. Now, one more thing I want to point out on this slide. Recall that the residual is equal to B minus A times the approximation, so A times xa. If I replace xa, no, I'm sorry, if I replace A, oops, if I replace A by its equivalent N minus P, then we get this. And now when you multiply N times xa, as we saw, N times xa is just equal to B. So N times xa gives us B. That cancels with this B, right? B minus B. And all that's left is going to be minus P times xa. Well, the two negatives cancel, so we end up with just this, P times xa. In other words, the residual for the initial estimate is simply equal to P times xa. Okay, so we'll use that on the next slide. Okay, let's try this out now. Try out the iterative method that we were looking at earlier. So remember, the way this works is, as on the previous slide, our initial estimate XA is going to be given, is going to be the solution to n times XA equals B, right? We solve using our approximation n to the matrix A. Okay, so, or in other words, x1, our first approximation, will be n inverse times b. Now, I could have written n sub a sub 1 or something, but I didn't want to get carried away with the subscript, so I'm just writing x1. So this is our initial approximation, and then the initial residual, as we saw in the previous slide, r1 is just equal to p times x1. Now we know that in theory, the true error, E1, error in our first approximation, satisfies the equation A times E1 equals R1. And so if we could solve that equation, we could get the exact value for E1, which would be A inverse times R1. However, we can't. We can't solve this exactly, but what we can get exactly is n inverse times R1, right? Using our approximation n to A. So we'll use this as our approximation to the error, and then we'll adjust our approximate value XA using this error, right? Only an approximate error. So, okay. So in the second iteration, what we're going to do is we're going to try to improve our approximation by defining a second approximation x2 equal to the first one plus the approximation to the error. Okay? Now, it turns out that there's an interesting relationship between x2 and x1 that is constant throughout the entire iteration. So what you do is you multiply both sides by n. On the left we get n times x2. On the right, n times this quantity. Now the thing is, n times x1, as we saw, that's just equal to b. Right? x1 is the solution to n times x1 equals b. So in fact, n times x1 is equal to b. If I multiply n times A inverse, it cancels, and that'll just leave an R1 as the second term. R1, you'll recall, was just p times x1. So what we get is this relationship between x1 and x2. n times x2 is equal to b plus p times x1. And so, in fact, this would be a much faster way of doing the iteration. Right? We don't even worry about the residuals. Just take b, add p times the previous estimate, and then solve for x2 using n, which remember is LU, the LU decomposition. So as I said, in general, this relationship holds for all subscripts, right? For all levels of iteration, for all n. Now it's just slightly more complicated to verify this, like for x3. But then once you get it for x3, it's pretty clear that it goes through. So I encourage you, if you're interested in this kind of thing, see if you can verify this formula for the case for x3, that n times x3 equals b plus b times x2. It's just a tiny bit more complicated, but pretty straightforward. Okay, so now that we've got this relationship, now finally we can look at the convergence behavior. Does this iterative procedure yield a sequence of xn's that actually approach the correct value, the true value, xt. Okay, so let's look at this. Suppose we want to calculate the error for the next approximation, right? The error for xn plus 1. So en plus 1 will be equal to the true value of t minus the n plus first approximation. Now we do something that's becoming familiar, I think. Here we multiply through by n. On the right-hand side, I'm going to replace n here by a plus p. Right? Remember, a equals n minus p, so sorry, did I say that right? A equals n minus p, so n equals a plus p. Right? So we plug that in, times xt, and also we know from the relationship on the previous slide, we know that n times xn plus 1 is always equal to b plus p times xn, right? P times the previous approximation. Now, if I expand this over here, a times xt is, of course, exactly equal to b, right? The original matrix A times the true solution will give us b. And then we have this term p times xt minus b and minus p times xn, and the b's cancel. If we factor out to p, we end up with this, p times xt minus xn, and of course xt minus xn is exactly en. So we end up with this relationship. N times e sub n plus 1 is equal to p times e sub n. Multiplying through now by n inverse, we get this relationship. The relationship between the errors at successive iterations. The error at iteration n plus 1 is n inverse times p times the previous error at level n. Right? So you can see that every time we do this, we multiply the previous error by n inverse times p. So in conclusion, if you start with the E1, the initial error for the first iteration, and every time you iterate, you multiply by a factor of n inverse times p, then by the time you get to en plus 1, you will have multiplied by n of those factors, right? And therefore, in general, we can say that en plus 1 will be equal to n inverse times p raised to the nth power times the original error, which is a constant. Therefore, we can say that the error will be approaching 0 as long as this factor has a norm which is strictly less than 1, right? As long as this condition is satisfied, then the norm of en plus 1 will be strictly less than the norm of n inverse times p raised to the nth power times E1, which is the norm of E1, which is a constant, right? So we're guaranteed to have convergence to the correct value, or in other words, that the error will be converging to 0 as long as that factor n inverse times p has a norm which is strictly less than 1. Okay, so if that condition is satisfied, well, let's see, under what conditions would we expect that to be satisfied? Well, if our n, which remember we're thinking of as being L times U, the LU decomposition of A. If n is sufficiently close to A, then the norm of P will be pretty close to 0, right? So if we can get a good enough approximation to A that the norm of P is sufficiently close to 0, then the smallness of the norm of P, that may make up for the whatever problems we might have in N or in A, right? So there's hope that, there's good reason to think that this will routinely be satisfied in the case when you're using N equals LU. LU should be a pretty good approximation to N, and P should be pretty, LU should be a pretty good approximation to A, to the original matrix A, and therefore P should be pretty close to 0, and you would routinely expect this to be satisfied in those cases. But it's interesting to note that now that we've developed this theory, we can apply it to any n and p as long as this inequality is satisfied. So we could take any approximation n to the matrix A, and then p would be the difference between A and n. And as long as this inequality is satisfied, we could use this iterative method to converge to a solution. Now, why might you want to ever do that? Well, you wouldn't want to do it in any of the cases we've looked at so far. Our matrices, we've been using pretty small matrices. You might want to do it in a case when the matrix A is extremely large, like maybe, 1,000 by 1,000 or something, got 1 million entries in it. With a matrix that's that large, even doing the row reduction method or the LU decomposition method could be time consuming, right? It could be difficult to do all those row reduction operations and carry it out on a really large matrix. So in those cases, of a really large matrix, that's one example where you might want to use simpler methods, and this iterative method is actually simpler. Think of it this way. The basic idea is that we always get the next iteration by solving the equation n times xn plus 1 equals b plus p times xn. So we take the previous iteration, we multiply by p, add b to it, and then solve this equation by somehow dividing out n, right, from the equation, and we assume that we've chosen n so that that's easy to do, right? So this might actually be an easy algorithm to carry out, an easy loop to perform at each iteration, or I should say an easy iteration to perform at each step of the loop, as long as n has been chosen wisely. Right? And then this would actually be a pretty easy algorithm to carry out. So I'm going to do a kind of a silly example of applying that to a particular case. In this case, I'm going to do it with a 2 by 2 matrix. Now, there's no reason you'd ever want to apply this method with the 2 by 2 matrix A. Right? It's just unnecessary. But I just want to show you how the thing works and how the theory gets applied. So with this A inverse is this. I worked it out on MATLAB. This is the inverse. And if you work out the norms, the norm of A is actually 8/15. That's the greatest row would be the first row. It adds up to 8/15. A inverse, the biggest row in absolute value, is the second row. It adds up to 70. So the norm, the condition number of A would be 8/15 times 70 comes out to be about 37 1/3. That's not dramatically bad. It's not particularly good. In fact, matrices like this, where the all the entries are kind of progressive fractions like this, where the denominator gets slowly larger in each row, which in fact is the kind of matrix I used to solve the Legendre polynomials, right? To find the Legendre polynomials, we solved matrix equations with coefficient matrices that look like this. In fact, these are kind of notoriously ill-conditioned, and in fact, this one, just a 2 by 2 matrix, this is kind of a big condition number for a 2 by 2 matrix, right? So, yeah, these do tend to be problematic type matrices, right? So if you had a really big one, the condition number might be quite large, and you might have to worry about that. But certainly at a 2 by 2 size, it's really not an issue. So what I'm going to do in this case is, for my approximation n to A, instead of using the LU decomposition, I'm just going to use L. Well, not exactly. I'm going to use A lower triangular matrix. Right, so I'm going to basically just take the lower triangular elements from A. I'm going to throw out the 1/5 and make that a 0. So I'm just taking the lower triangular part of A. Therefore, N is, in fact, a lower triangular matrix, and we can easily solve equations involving N, like Nx equals B, can easily be solved just by using forward substitution. Right? This is a very easy matrix in which to solve linear equations. For the record, the actual inverse of n is this. It's quite simple, right? Notice how it's dramatically simpler than the inverse of A, right? So in this case, just by making n into just taking the lower triangular part of A, it does in fact make the inverse matrix radically simpler. And in fact, if you do the calculation, let's see, P would be, it would be all zeros except for negative 1/5 up here. And if you do the calculation, the norm of n inverse times p would be 21 25ths, which is strictly less than 1, although it's kind of high, right? I mean, it's not much less than 1. So what we can expect is that using this iterative method, we should be able to get the solution this way, but it might be slow because this factor is not dramatically less than 1. So it might take a while for the iterative method to converge, but it should get there eventually. Okay, so now I'm going to switch to MATLAB in a minute, but let's just kind of review what we're going to do now. One thing you can do is you could just take x0, the first approximation, to simply be 0, and then nx1, using the iterative formula. Remember, we said that at each stage, the n times the x sub n plus 1 will be equal to b plus p times x sub n, right? N times the new approximation will be equal to b plus b times the old approximation. In this case, when x0 is 0, this just gives us the same x1 we'd used before. It's going to be n inverse times b. Then for x2, we solve this equation, right? Again, using the same pattern, n times x2 equals b plus p times x1. We solve this by multiplying by n inverse, right? Now multiplying by n inverse is easy because n inverse is easy, right? We actually worked it out. It's a pretty simple matrix, and so on, right? So at each step of the iteration, we really just perform n inverse times b plus p times the previous step. So what I'll do in MATLAB is I'll define a function that'll just perform that iteration. So it'll just be a function that takes the old approximation for x, multiplies it by p, adds b, and then multiplies that sum times n inverse. And then we can just keep applying this iter function to the previous value of x to get the next value of x. Okay, let's switch over to MATLAB. Okay, so let's try this out on MATLAB. First, I'll enter the A matrix. Let's see, I got it stored here somewhere. Oh, here it is. There we go, A. Oops, no, that's not the one. What did I do? Oh, I see, okay. There's A. Okay, so there's the A matrix. And the N matrix, I'm going to get, well, actually, tell you what, I'll just modify A. I'm going to put a 0 in the upper right. So N will be that. Right, that's a lower triangular matrix. I think what I'll do is also I'll just enter N inverse by hand. Right, so N inverse was 3, 0 in the first row and negative 4.27 in the second row. So that's N inverse. Now, I also want to define this function, the iter function, right? So yes, that is, I'm going to multiply N inverse times b plus p times whatever the input value is. And the input value will be, the previous approximation to x, and the output value will be the new approximation to x. Now, I'll tell you what, we should have some b. Let's make up some b. Maybe I'll just make b nice and simple. B, the constants on the right-hand side, they'll just be 1, 1. Okay, so we're trying to solve a times x equals b. Might be helpful to get the true solution. You can do that by left dividing a into b. Right? So you can use this left divide operator in MATLAB in a situation like this too. MATLAB will understand that you're trying to multiply A inverse times the on the left side of B, and MATLAB will be smart enough not to compute A inverse. It'll actually try to do it using the LU decomposition. So MATLAB is smart enough to interpret this as do LU decomposition and use that to solve the equation a times x equals b. Right? It'll understand it that way. Okay, so the correct answer seems to be negative 7.5, 17.5. Interestingly, there does seem to be a bit of an error, right? I'm guessing that these numbers are supposed to, the true answer is exactly negative 7.5 and negative 17.5. Why don't I call that xt? Let's see, xt, does that work? Negative 7.5 and 17.5, and if I multiply a times xt, do I get, what did I do? Oh, I'm sorry, I forgot xt is a column vector, so I had to put a semicolon there to make it a column vector. That's better. Let's try that. Yep, it works. So the exact answer is, in fact, negative 7.5, 17.5. Notice that when MATLAB solved it, presumably using LU decomposition, there was an error, right? It actually it did introduce an error, so the answer was not perfect. Okay, now let's try it using the iterative method. So I defined n. Oh, I should also define p. Remember, p is equal to n minus a. Okay, so there's my p. And let me recall. Yeah, okay, so I already defined the iter function, right? So let's just start off with an x value. Like x, again, I'll just assume x is just a 0 vector, okay? And then when we apply the iteration once, I can update x by applying the iteration to the current value of x. Okay, so the first approximation it gets is 3, 2.8. Let's repeat that. Okay. At least at this point, the first entry has the right sign. Do this a couple more times. Wow, it seems to be getting closer to the correct answer of negative 7.5, 17.5, but it does seem to be converging awfully slowly. So let's try to speed things up a bit. Let's create a for loop. Let's say for I, let's do it, say, I don't know, 20 times. How about that? For I goes from 1 to 20, we'll just do this same line, x equals x iter, and then end the loop. Okay, so we did get pretty close at the end here, right? In fact, why don't I do it another 20 times? Yeah, now we're getting really close, right? So we're within, it's accurate to, 2 decimal places, right, of the correct answer. So it does work, but as we feared, it did converge very slowly. But the main thing is that it did converge. That's the good news, right? So this kind of confirms the theory that as long as that factor, the norm of n inverse times p, as long as that is strictly less than 1, then this method will converge to the correct answer. And as I said, this method, you wouldn't use it in a problem like this, but you might use it in a problem where you have a gigantic matrix A that you're trying to solve the equation AX equals B. Then an iterative method like this might actually work better than trying to do Gaussian elimination on a huge matrix.